This is Krishna from Department of Mechanical Engineering, DBS Institute of Technology. Today we can discuss solidification of casting. Unit 1, solidification of casting. So first, introduction to solidification. Solidification of casting may takes place at constant temperature over a range of temperature or both depending upon the composition of metal. During this process of cooling, the solid metal cools to room temperature. It observes that during solidification of casting. Solidification mechanism is essential for preventing defects due to shrinkage. As soon as the molten metal is poured in the sand mold, the process of solidification starts. During solidification, cast forms develop corrosion and acquires structural characteristics. The mode of solidification affects the properties of the casting achieved, acquires a metallographic structure which is determined during solidification. The metallographic structure consists of grain size, shape and orientation, distribution of alloying elements, underlying crystal structures and its imperfections. Volume shrinkage or contraction occurs during these three stages: liquid contraction or shrinkage. Liquid contraction occurs when the metal is in liquid state. Solid contraction, solidification contraction occurs during the change from liquid to solid. Solid contraction occurs when the metal is solid. Solid contraction occurs after solidification. Solid contraction does not influence shrinkage defects. Next, concept of solidification on casting. A metal in molten condition possesses high energy. A metal in molten condition possesses high energy. As the molten metal cools, it loses energy to form crystals. Since heat losses is more rapid near the mold walls than any other place, the first metal crystallites called nuclei form here. Nuclei formed as above tend to grow at the second stage of solidification. The crystal growth occurs in the dendrite manner. Dendrite growth takes place by the evolution of small arm on the organical branches of individual dendrites. Slow cooling makes the dendrites to grow long way. Fast cooling causes short dendrite growth. Since eventually dendrites become grain, slow cooling results in the large grain structure and fast cooling in the small grain structures in the solidified metal. As solidification processed, more and more arms grow on an existing dendrites and also more and more dendrites from until the whole melt in crystallized. So figure shows the formation of dendrites. Next, solidification of pure metals. Pure metals melt and solidify in single temperature, which may be termed as melting point or freezing point. If a number of temperature measurements are taken at different times, while pure metal is cooled under equilibrium condition from the molten state till it solidifies. A time temperature plot will be look at the figure here. If a pure metal cools rapidly when it is very pure and does not contain any impurities as nucleus to start crystallization, it may cool as figure number 3. So in see the figure, equilibrium condition is figure here, supercooling in figure B. Next, solidification of pure metal. Pure metals generally possess excellent thermal and electrical conductivity. So example, copper and aluminum. High ductility, high melting point, low yielding point, and tensile strength. And better corrosion resistance as compared to alloys. So these are all the pure metals. As metals possess high melting points, they exhibit certain difficulties in casting. Difficulties during pouring, occurrence of several melt mold reactions, metal mold reactions, greater tendency towards cracking. This mode of solidification which may produce defective castings. Above freezing points, the metal is liquid and below freezing point is solid. So the graph is between temperature and time, solidification of curve for metals. So first pouring the temperature, it decrease the temperature in thermal arrest. So the temperature is constant. So the corner point is equilibrium freezing temperature. So next, cool down the temperature. So the above figure or curve, the following observations can be made. So liquid metal cools from A to B, from starting point to this point. From B to C, the melt liberates latent heat of fusion, temperature remains constant. From B to C is horizontal line. The horizontal line is B to C. The temperature remains constant. The liquid metal starts solidifying at B. It is partially solid at any point between B and C, and at C melts purely solid. From C to D, the solid metal cools and tends to reach room temperature. That means below line, C to D. The solid metal cools tends to room temperature. The slope of AB and CD depends upon specific heat of liquid and solid metals respectively. If a pure metal cools rapidly or even otherwise when it is very pure and does not contain immunity at all, such as nucleus, to start crystallization, it may cool as per nucleation of solid doesn't start at point B, that is normal solidification temperature, but it does so at B after the liquid metal has supercooled by an amount delta T. The phenomena is known as supercooling or undercooling. Besides pure metals, supercooling may occur in alloys. Example, grey cast iron. Solidification of alloys. Alloys metal process. High tensile strength, better high temperature strength, better corrosion resistance, improved machinability and workability, low melting point, improved castability. Main types of alloys: solid solution alloys, eutectic alloy, pretextic alloys. Solidification of alloys from the curve. So the above curve shows the cooling curve from the binary solid solution alloy. From A to B, the alloy is in liquid state. From A to B, the alloy is in liquid state. So this is the figure A to B. The solidification start at B and complete at point C. So solidification start at point B and completed at point C. Next, unlike pure metals, solidification occurs throughout the temperature range from TB to TC. Next, latent heat of fusion is liberated gradually from B to C, and it tends to increase the time required for the solidification. Next, special casting process. So in special casting process, so first is shell molding. Shell molding is an efficient and economical method for producing steel castings. The process is developed by Harkonnen in Germany during the World War II and is something referred as the Kroning shell process. Something referred to the Kroning shell process. Procedure involved in making shell mold. A metallic pattern having a shape of the desired casting is made in on half from the carbon steel material. Pouring element is provided in the pattern itself from the figure A. The metallic pattern is heated in an over to a suitable temperature between 180 degrees to 250 degrees centigrade. The pattern is taken out from the oven and spread with a solution of lubricating agent because silicon oil are split to prevent the cells formed in large state from sticking to the pattern. The pattern is inverted and is placed over a box as shown in figure P. The box contains a mixture of dry silica sand or zinc sand and resin binders 5% based on sand. The box is now inverted so that the resin sand mixture falls on the heated face of the melting pattern. Heated place of the melting pattern. The resin sand mixture gets heated up, softened and sticky to the surface of the pattern from the refer figure C. After a few seconds, the box is again inverted to its initial position so that the loose resin sand mixture fall down, leaving behind the thin layer of the shell and the pattern face. So refer figure D. The pattern along with the shell is removed from the box and placed in the oven for a few minutes, which further harden the shell and make it rigid. The shell is in the stripped from the pattern with the help of ejector pins. They are provided on the pattern. Refer figure number E. So another shell half prepared in the similar manner and both the cells are assembled together with the help of bolts. Clips are glued to form a mold. The assembled part is taken placed in the box with suitable baking sand to receive the molten metal. Refer figure F. After the casting solidifies, it is removed from the mold, cleaned and finished obtain the desired shape. Advantages: better surface finish and dimensional tolerance, reduced machining, require less boundary shape, semi-skilled operators can handle the process easily, shell can be stored for extended period of time. Disadvantages: initially, the melting point pattern has to cast to desired shape, size and finish. Size and weight range of casting is limited. So these are the figures. One by one we can see. So figure A, B, C. So finally, shell will be prepared. Shell molding steps involve process by seeing the figures. Next, investment mold. Investment mold, also called as precision casting or last wax process, in an ancient method of casting complex shapes like impellers, turbine blades, and other aeroplane parts that are difficult to produce by other manufacturing techniques. So that's how we can use investment casting. So there are various steps involved in this process. So step one, die and pattern making. A wax pattern is prepared by injecting liquid wax into a prefabricated die having the same geometry of the cavity of the desired cast. Several such patterns are used in the similar manner and then attached to wax gates and spur by means of head tools or melted wax to from the tree as shown in figure 2. So this is the wax pattern. So wax ports for the funnel top of the pattern. Next step 2. pre-coating wax pattern. The 3 is coated by dipping into refractory slurry, which is a mixture of finally ground silica flour suspended in ethyl silicate solution. So this name is, another name is binder. The coated 3 is sprinkled with a silica sand and allowed to dry. So we can see the refer 3 and 4. See the figures in 3 and 4. Step number 3, investment. The pre-coated tree is coated again, referred as investment, by dipping in a more viscous slurry made of refractory flour. So refractory flour means used silica or aluminum, etc. And liquid binders, sodium silicate, colloidal silica, etc. And dusted with refractory sand. The process of dipping and dusting is repeated until a solid shell of desired thickness, about 6 to 10 mm. 6 to 10 mm is achieved. Note, the first coating is composed of very fine particles that produces a good surface finish, whereas the second coating, which is referred as investment, is coarser so as build up the shell of desired thickness. Next, dye waxing. The tree is placed in the investment portion and heated in a oven to above 300 Fahrenheit. The wax melts and drops down, leaving a metal casting that will be filled later by the molten metal. So we can refer figure number 5. Reheating the mold. The mold is reheated to about 1000 to 2000 degree Fahrenheit or 500 to 1100 degrees centigrade to remove any residues of wax and at the same time of harden the binder. Melting and pouring. The mold is placed in the flask supported with a baking material and the liquid metal of the desired composition is poured under gravity or by using air pressure depending on the requirement. Then refer figure number 6. After the metal cools and solidifies, the investment is broken by using chisels or hammers and that casting is cut from the system, cleaned and finished. So we can refer figure number 7. So overall figures we can see the entire process steps. Next, advantages. It gives good surface finish and dimensional tolerance to the casting. Eliminates machining of cast parts. Additional machining is not normally required. Wax can be reused. Parts of great complexity and intricacy can be cast. Disadvantages. Process in expensive, size and weight range of casting is limited. In some cases, it is difficult to separate the refractory from the casting. Requires more processing steps. Pressure die casting. Pressure die casting, often called die casting, is a casting process in which the molten metal is injected to the die under high pressure. The metal being cast must have a low melting point from the die material, which is usually made from steel or other alloys. Hence, this process is best suitable for casting non-ferrous metals, although the few ferrous metals can be cast. The two basic methods of die casting includes hot chamber die casting process, cold chamber die casting process. So first we can discuss it in hot chamber die casting process. Figure shows a gauze neck type of hot chamber die casting machine. In this process, the dies are made in two halves. One half is called fixed die or stationary die, while the another half is called movable die. The die are aligned in position by means of ejector pin, which also help to eject the solidified casting from the dies. Steps involved in the process. It provides cast iron goes neck in submerged in the reservoir of molten metal, where the metal enters and fills the gooseneck by gravity. The gooseneck is raised with the help of link, and the neck part is positioned in the part of the fixed part of the die. Composed air in the blown from the top, which forces the liquid metal into the die cavity. When the solidification is about to complete, the supply to compressed air is stopped and goes neck in lowered back to reservoir the molten metal for the next cycle. In the meantime, the movable die half open by means of ejector pin, forcing the casting in the die casting. The die half close to receive the molten metal from the next casting. Hot chamber process is used to casting metals like zinc, tin, magnesium and lead based alloys. So this is the steps in hot chamber casting. The next, cold chamber die casting process. In hot chamber process, the changing unit goes neck resides in the melting chamber, whereas in cold chamber process, the melting chamber is separate and molten metal is changed into the machine by means of ladles. Cold chamber process is employed by casting materials that are not possible by the hot chamber process. For example, aluminum alloy, with the steel structure of the hot chamber mission, and as result there is a combined iron pickup by aluminum. This does not happen in the cold chamber process as the molten metal has a momentary contact with the structure of the mission. Figure shows the cold chamber die casting process. The mission consists of a die made in two halves. One half called is fixed die and stationary die, while the another half is called movable die. The dies are aligned in positions by means of ejector pin, which also help to eject the solidified casting from the dies. Steps involved in process. A cylindrical shaped chamber called cold chamber. Because it is not a part of melting or charging unit, unlike in heat chamber process, is fitted with the freely moving piston and is operated by means of hydraulic pressure. A measured quantity of molten metal is poured into the cold chamber by means of ladles. The plunger of the piston is activated and progresses rapidly, forcing the molten metal into the die cavity. The pressure is maintained during the solidification process. After the metal cools and solidifies, the plunger moves backward and the movable die half opens by means of ejector pins, forcing the casting from the die cavity. The cold chamber process is slightly slower when compared to hot chamber process. So you can see the above figure, cold chamber process. So advantages of die casting process. Process is economical for large production quantities, good dimensional accuracy and surface finish. Thin sections can be easily cast, near net shape can be achieved. Disadvantages: high cost of dies and equipment, not economical for small production quantities. Progress not preferred for ferrous metals. Part geometry must allow easily removable from die cavity. Next, centrifugal casting. In centrifugal casting is a process in which the molten metal is poured and allowed to solidify in a removing mold. A centrifugal force due to removing mold hold the molten metal against the mold wall until it solidifies. The material used for preparing molds may be cast iron, steel, sand, or graphite for non-ferrous casting. The process is used for making casting of hollow cylindrical shapes. The various centrifugal casting techniques involve true centrifugal casting, semi-centrifugal casting, and centrifugal casting. So first we can discuss true centrifugal casting. The true centrifugal casting is used to produce parts that are symmetrical or about axis, like that of pipes, tubes, rings, liners, bushings. The outside shape of the casting can be round, octagonal, hexagonal, etc. But the inside shape is perfectly theoretically round around the radial symmetric forces. This eliminates the need of force for producing hollow casting. The figure shows the true casting process. Steps involved in the process. The mold of the desired shape is prepared with metal and the walls are coated with refractory ceramic coating. The mold is rotated around the axis at high speeds in the range of 300 to 3000 rpm. A measured quantity of molten metal is poured into the rotating mold. The centrifugal force of the rotating mold throws the liquid metal towards the mold wall and hold the molten metal until it solidifies. The casting cools and solidifies from its outer surface towards the axis of the rotation of the mold, thereby promoting directional solidification. The thickness of the casting obtained can be controlled by the amount of liquid metal being poured. An inherent quantity of true centrifugal casting is based on the fact that the non-metallic impurities in casting, being less denser than the metal, are forced towards the inner surface of the casting due to centrifugal force. The impurities can be machined later by a suitable machining process. The mold may be rotated horizontally or vertically. When the mold is rotated about horizontal axis, a true cylindrical inside the surface is produced. If rotated on the vertical axis, parabolic inside surface is produced. Coarse and gating or preserving systems are not required for this process. Semi-centrifugal process. In semi-centrifugal casting process is used to produce solid castings and hence required a core to produce hollow cavity. The process is used only for symmetrically shaped objects and the axis of rotation of the mold is allowed vertical. Air blanks, stayers, wheels and pulleys are commonly produced parts by the process. The figure shows the process to process while spread casting. Figure shows the process to process a wheel shaped casting. Steps involved in the process. The mold is prepared in the usual manner using core and drag box. The mold cavity is prepared with the central axis being vertical and concentric with the axis of rotation. The core is placed in the position and the mold is rotated at suitable speeds, usually less than true symmetrical casting process. The centrifugal force produced due to the rotation of the mold causes the molten metal to fill the cavity to produce the desired shape. Next, last one, centrifugal process. In true and semi-centrifugal process, the axis of mold or cavity coincide with the axis of rotation. Whereas in centrifugal process, the axis of the mold cavity does not consider with the axis of rotation. The mold is designed with a part cavities located away from the axis of rotation. Hence, this process is suitable for non-symmetrical casting. Figure shows the centrifugal process. Steps involved in the process. Several mold cavities are arranged in a cycle or connected to central downspur through gates. The axis of the downspur is common to axis of rotation of the mold. As the mold is rotated, the liquid metal is poured down the spur, which fits the melt into the mold cavity under centrifugal force. The rotational speed depends on the number of factors such as the molding medium, size of the casting, type of metal being poured, and distance of the cavity from the central axis. Centrifuging is done only about the vertical axis. Thank you.